Welcome to the video in which we'll start the introduction to special relativity. Now, before running into general relativity, we need to make sure that we understand very well special relativity that came before and sets the basis for the theory of relativity. But first, let's just try to address some perhaps common misconceptions that people have about special relativity. And then we will proceed to the postulates of special relativity. And from those postulates, we're gonna derive everything else. So first of all, I have here a phrase, a sentence, a statement, and I want you to think about it, whether you think it's true or false, based on the knowledge of special relativity you've seen in the past. Now, I wrote here, the speed of light measured by all observers is the same, and then equal to c. What do you think? Is that true or false? Cast your votes. Well, let's see what the reveal is. And it is false. This statement is not true.
A point of clarification before we continue. While it is very fun and clickbaity to say that those statements are false and then keep going and laugh about it, it is true that there's a number of subtleties related with what one means when talking about the speed of light. These subtleties will be addressed more in depth when we see non-inertial frames in special relativity, where we will actually look at the speed of light as described from non-inertial frames. For now, suffices to say that what we call the speed of light, coming from an experiment, is something that we need to agree on. But for the purposes of these statements, I am referring to the amount of length covered by light over the amount of time that it takes to cover it from the reference point of the experimenter. So saying that the speed of light would be the same for all observers and everybody would measure the speed of light would be a very, very dangerous statement that in the best case scenario needs to be enormously qualified, and in the worst case scenario is just plain wrong. Now, that clarified, let's continue.
So let me try to improve it a little bit and see if it becomes right, all right? All right, I have a new statement here. In the absence of gravity, all observers measure the same speed of light. What do you mean by that? Well, maybe you were thinking perhaps there's a catch, general relativistic catch, so curvature of space-time will make, well, yeah, in absence of gravity, so nothing to take into account regarding gravity. What do you think? Is that true or false now? Okay, cast your votes, and let's make the reveal. It's false as well. It's also not true. All right, well, okay, I need to work harder to get to something that I can call true statement in the context of special relativity. All right, let's see this one. I added a keyword here, right? And now this reads, in the absence of gravity, all inertial observers measure the same speed of light, c. Now, what does inertial mean? Inertial means that you don't experience any forces as per Newton's first law. So you are in a constant state of motion. Okay, you experience no forces. If you experience no forces, that's an inertial observer. So, in the absence of gravity, all inertial observers measure the same speed of light. And that statement is, again, within the context of special relativity, is true. Finally, we found a true statement within the context of special relativity. Now, this is something that, again, will be one of the postulates of special relativity. We'll formulate it much better, and we will talk a little bit about where it comes from. But this is the right formulation. So it is definitely not true that in special relativity, the speed of light, every observer will measure the same speed of light, okay? Which is c. Only inertial observers will. That's what we will demand. We will talk a little bit about the subtleties about that. Maybe locally they do, or maybe we'll see when we see non-inertial frames in special relativity. And that is something that leads us to the next statement that is usually believed, because historically at the beginning was kind of believed to be the case, but it's totally not the case. Let's write another statement here. All right, so we have this statement, special relativity only handles inertial frames. In order to handle non-inertial frames, you may need general relativity. How is that statement? Do you think, what do you think it is? Is it true or is it false? Well, as you may already have guessed, it is false, because I already said it. Totally not true. We can handle non-inertial frames as long as there's no gravity. Non-inertial frames handling, it's okay within special relativity, and we will see it. And in particular, I will introduce you to a little bit of non-inertial frames in special relativity. And this is that will be basically the end of the block on special relativity.
The next thing we're going to see is the postulates of special relativity.
All right, so first, before writing the postulates, let me define what a reference frame is. A reference frame is a spatial coordinate system where the position of point-like particles can be specified, and a clock. So a reference frame is made out of spatial coordinates relative to some origin, and a clock, something that can measure time. All right, cool. Now, let me define inertial reference frame, although I already did, but let me just quickly write it here. So the definition of inertial reference frame is a reference frame from which a particle stationary at its origin, so the reference at which the frame is actually nailed to, experiences no forces. And that is actually easy to check, because you can check if you experience no forces. You can have an accelerometer. Accelerations are very easy to measure. So if the accelerations that you measure are 0, then you're in an inertial reference frame. Okay, that you could be a reference for an inertial reference frame. All right, with these two definitions, we can write the postulates of special relativity. Let's begin with postulate 1. The first postulate is called the principle of relativity. It tells you that in the absence of gravity, all the laws of physics are identical in all inertial reference frames. Important the word inertial in here. Now, this postulate is the same as in Galilean kinematics and Newtonian mechanics before relativity. So this postulate, Einstein didn't change, it kept. It's a very obvious postulate of physics that we see that our choice of where to look at when we describe a physical system should not change the behavior of the physical system. All right, that is not change. The real change happens at the level of postulate 2. Let's see what it says. Postulate 2 tells me that the speed of light in vacuum, which we call c, is constant and the same from all inertial reference frames. Now, that's the one that is groundbreaking, because in Galilean kinematics, velocities compound. And if I'm moving at a reference frame, if I measure the speed of light and it's c, and then somebody else is driving in a car and measures again, the speed of light should compound with the speed of the car. But Einstein is saying, no, let's postulate that it doesn't. Let's postulate that the speed of light is the same for everybody, and it's c. And that is groundbreaking. That is what changes. That is the only little change, and it's inspired by the Michelson-Morley experiment. So let's see what happens if I go with these postulates and try to derive the transformation between reference frames. Okay, what is the modification that I have to do to mechanics and kinematics if I accept these two postulates to start with? Shall we see what the consequences are? All right, let's see them. All right, let's calculate what are the consequences of assuming postulate 1, which is, remember, that the speed of light will be the same from all inertial reference frames. All right, let me take an arbitrary reference frame, one particular reference frame, and that reference frame establishes coordinates t and x. So it gives me a time coordinate and a position coordinate, right? And then we define the space-time interval, delta s squared, that's the space-time interval, this thing here, okay, between two events, two things that happen. At time t1, position x1, and another thing that happens at time t2, position x2. For example, so an event is something that happens at a given time at a given point. So imagine, E1 could be me jumping, so you see, that happened at a given time, at a given position where I am. That could be E1. And E2 could be, for example, the camera registering my jump. Of course, it happens at a different time in a different position in that frame, right? Because light takes a while to propagate from me jumping to the camera to be registered, okay? So T1, X1 when I jump, T2, X2 when the jump is registered by the camera, for example. We can represent it in a space-time diagram. So a space-time diagram, I put T on the y-axis, X on the x-axis, in 1 plus 1 dimension here, just to simplify. And I also added a C here to make the same dimensions for the axis. So if that is, so this is C T1 X1, that's the first event. And this is C T2 X2, that's the second event, okay? And this is CT, and this is X, right there. Okay, so the space-time interval I define as minus c squared delta t squared, which is just the difference between times squared, plus the distance between the events in space squared in that reference frame, in that particular reference frame, all right? So now, important, in this object, what is important is I define it with different signs for time and space intervals. Typically, there are two ways of choosing these signs. I can put the minus here, or I can put the minus here. That is called, one is called the East Coast Convention, the other one is called the West Coast Convention. The East Coast Convention is actually the one that I have here, and the West Coast Convention is putting the minus sign here instead of that one. The West Coast Convention is actually popular among particle physicists and high energy physicists, whereas the East Coast Convention, it's common among people who actually work with general relativity, and thus, for example, quantum field theory in spacetimes, And that's definitely the one that I do. That's what my research is about. So this is the signature, the metric signature that I use. They are not compatible. So if you pick one, you have to stick with this one forever to calculate everything you do. But both are correct in the sense that there's no, in principle, wrong choice. It would work either way. Now, if you ask me, well, I have my own opinions. In fact, I'm gonna nickname, both of them are okay, you know. I'm gonna nickname the East Coast Convention, the one that I use, I'm gonna call it the right convention. And the West Coast Convention, I'm gonna call the wrong convention. Okay, but those are nicknames. If you want me to actually give you arguments why I think this one is actually the right one and the one that everybody should use, I do have arguments, but I'm not gonna give them in this video. You're gonna have to ask me in the live sessions, all right? But for now, let's go with either works, but in this course, I'm gonna go with what is called the East Coast Convention for choosing signs in the space-time intervals, and later on the signature of the Lorentzian signature of the metric, okay? But that said, that out of the way, this thing would exist for all events, right? Any two events, we can compute the space-time interval between them. Now, in particular, to help me impose postulate 2, which is the fact that the speed of light should be the same for all inertial reference frames, let me pick the two events in a particular way, okay? I'm gonna pick the two events related by the propagation of light. For example, me jumping and the camera receiving the signal. Because me jumping and the camera receiving the signal are separated in space, right? But are separated in time by an amount equal to the space that it is divided by the speed of light, right? Because the speed of light, so it takes light to get to the camera. Well, it's space divided by the speed at which it goes, which is the speed of light. All right. Now, if I take two events related by light, what would happen? Let's see it. All right. So if c is the speed of light as measured in the frame tx, which is the frame we're using here, and the two events are connected by the propagation of a ray of light, then we know that, of course, the amount of distance between the two events is exact, which is, remember the two events, me jumping here and the light being received at the camera lens. Those are two events connected by the propagation of light. So the amount of space covered between the events 1 and event 2 is exactly equal to the speed of light multiplied by the amount of time that it took, all right, to get there. So if that's the case, then I know that the space-time interval in this frame is 0. All right, so far so good? All right, so let's take this in our memory units, okay? And now let's see what happens when I describe this from a different reference frame. If we consider now a different inertial reference frame, so for example, a friend of mine that also has their clock has a different time because they're delayed with respect to me, for example, and is set somewhere else and facing a different direction. So for that person, space and time have different coordinates, right? Their watch has a different time reading, and the distances are different. I mean, the distances, no, the coordinates are different, right? So imagine now that I compute in this other reference frame, I compute, well, I know what is the space-time coordinates of the first event, me jumping, and the second event, the light from my jump arriving to the camera, right? It's the same event, E1 and E2. Now they have different coordinates because the person has a different watch, which is delayed with respect to mine, and is at a different distance. So Tx2 prime and x1 prime will be different from x2 and x1, and t2 prime and t1 prime will be different from t2 and t prime. Okay? Now we can compute the space-time interval for that frame, and I call it for now delta s prime square, and it would be this quantity here. Now, while all these quantities, with a square, of course, while all these quantities are different, t2 prime, t1 prime, x2 prime, x1 prime from the previous one, and even if the speed of light changes in that frame, that's why I call it c prime square, what is true is that the two events are connected by light. So in that frame, it would also be true that delta x prime square equals c square prime delta t square. So basically this is just saying that prime, right? So has to be true that delta x prime square has to be equal to c prime square delta t square, because all that is saying is that the two events are connected by the propagation of the speed of light. This is saying, with a prime of course, this person is saying that the amount of space that the light had to cover has to be equal to the speed of light multiplied by the amount of time that it took to get there. All right, that is true. That is universally true in all frames, because it means that the light arrived to the camera. It's describing the same thing happening, right? And if that's true, that has to be 0 as well. Okay, so now we get this expression here, and we can combine these two expressions. Let me write them together. All right, so we have, remember that by computing what we define the space-time interval between two events, in this case was me jumping and the light from my jump actually hitting the camera, and as described from two reference frames, we got independently that the two reference frames, this quantity, the space-time interval, has to be 0, or both of them. And of course, if they're both 0, they're equal to each other as well. Now, again, remember that this is true not for relativity, it's true for Galilean mechanics, Galilean kinematics as well. Why? Because this is just the expression of the fact that I jumped and the light propagated to the camera. So in any frame that you measure that, it has to be true that the amount of time that it took the camera, the light to propagate from me to the camera, has to be equal to the amount of space divided by the speed of light. Speed of light may be different in different frames, and definitely the coordinates will be different in different frames, but this has to be true always. So we haven't applied yet postulate 1. Let's apply postulate 1. So if we apply postulate 1, it tells me that the speed of light is the same from all inertial reference frames. What does that mean? Well, that means that this prime here, I can remove if I assume postulate 1, which is a crazy postulate but comes from experiment. The experiment tells me that maybe the speed of light is the same from all inertial reference frames. So C equals C prime. That's the only thing. That's where relativity entered the picture. So far, it hasn't entered. Now it's invited. The door is open and all the monsters come in. So let's see what the consequences are of that innocent change. Now let's make the following observation. The possible transformations between reference frames, remember, are, let's write them here. We have 3 rotations, 3 independent rotations that could happen between the reference frames. They could be rotated with respect to each other. We also have 3 independent translations, right? Translation X, Y, and Z. I mean, basically my friend could be in a different position. It could be related by one-time shift, which is the fact that the watch of my friend is delayed with respect to mine, for example. And it could be related by 3 boosts. So 3 independent boosts. So there could be some velocity. My friend could be in a car looking at the whole thing happening with some speed, and we can always decompose any boost in 3 independent boosts. For example, X, Y, and Z. Velocity X, component X, Y, or Z, something like that. These are the differences between the frames, but this equation here that we established will inform us about one of them in particular. Why? Well, because, this thing is, you can tell that it's invariant under rotations. Here we have a distance. So if the difference between these two is a rotation in the distances, in the positions, right? The difference between the two square is invariant under rotations, is the magnitude of the distance between them. 3 translations, same thing. This is the length between them, the magnitude. So that thing is, if I move it like that, it's invariant. One-time shift. Yeah, sure, that's also invariant, because if the 2 times have a constant value of delay of the clock with respect to mine, it's gonna be disappearing when I subtract, right? So I don't care about the time shift. What I care about though is what happened with the boosts. So let me summon what we remember the rule of transformation for the Galilei boosts, okay? Just to remember it and compare. Let's do it. All right, so Galilei. Dirty Galilei. So this is the typical Galilei boost that you may remember, which is basically telling you, right, if you're in a car at constant speed, I mean, if my friend is in a car at constant speed, which has to be an inertial frame, then I know that the position in the new frame will be the old one, subtracting the velocity that this person moved by the time times the time that the person's been moving, right? That makes total common sense. Now, let's keep that for comparison, and then let's work out the boosts, the form of the boosts, the form that the boost will have to have in order for this to be true. Now, if I do this, if I substitute this here, then that will give me a wrong equation. This equality cannot be satisfied if I substitute the Galilean boost. Substituting this into that will give a mathematical inconsistency. So if that is true, which comes from postulate 1, this cannot be the transformation. Let's compute what the transformation should be instead. to find the transformation, I'm gonna be assuming two more things. Two is a mystery assumption, because it's deep, and it's usually swept under the carpet, and it should be at the level of postulate even. Although, I mean, well, we'll talk about it when we get there. Assumption one is very innocent, saying that the difference between the two frames is a constant speed, it's in an inertial frame, but basically saying that there's no rotation between them or translation, just to simplify, and because we would not be able to extract any information from it, considering that difference. So let's simplify and assume that the only difference is some speed v, and that means that the origin of the prime system, so the origin of the prime system is the vector 0 in the prime system. That is, you see, the coordinate in the prime system of the origin of the prime system is the 0 vector, has the trajectory vt in the unprime system, right? The center of the reference frame is moving in the car. That's what it's basically saying. So it's just basically saying that at time 0, my friend was here with me and then moved with the car after time 0. That's just without loss of generality, in the sense that, well, the difference between all those is between that and a general transformation is a possible rotation, a possible translation, and a time shift, which is trivial. So to find the transformation for the boosts, it's enough to consider this. Now that one is very innocent. The second one, though, is not innocent. Let's see it. Let's summon it. Ooh. The transformation has to be linear. Now, what do they assume? Why do I force that the transformation has to be linear? Well, that's a really good question. We will talk more about it in a little bit, but this is a very important assumption. To find the Lorentz transformations, you need to demand that the transformation is linear. And what is the physical justification for a linear Lorentz transformation? That is a very deep topic, okay? And we will get there. Well, I will mention something about that, but this is usually swept under the carpet. We need to assume the transformation to be linear, okay? In order to find the Lorentz transformation that Einstein found. So this could be at the level of postulate 2, so it's 2.5 postulates in a way. All right, what happens if that's the case? Well, now we need to get our hands a little bit dirty and do some calculations. I'm gonna just lay it out, you finish it, okay? But let's see what the calculation would tell us. So assuming the transformation is linear is doing this. But of course, I simplified a tiny bit, which I assume without loss of generality that the speed goes in the direction of x. So I call my x direction the direction of the speed. I don't need to do that to derive this, it's just to simplify the calculation. You could actually do it fully and find the full Lorentz transformation, or you can just do it with one coordinate and then rotate to an arbitrary direction to get the general one. So I wrote t prime and some arbitrary linear transformation of x and t. You see that it's linear, one coefficient for x, which is the product of these two functions that I write here of the velocity, and one coefficient for t. They're independent, right? One is gamma f and one is just gamma. They're two independent coefficients. They only depend on v because, of course, we assume here that the only difference between the frames is v, okay? And now this one, of course, is also a general transformation, and you may say, why don't you have a different coefficient for the x or for the t? Well, because in this case it has to be true that x of the origin of the prime has to be vt, and therefore that fixes one of the constants in here. All right, so if we assume that the transformation has this form, which, by the way, you can tell here the Galilei transformation I didn't write, but the Galilei transformation tells me that t prime is equals t. Time is absolute in Galilean relativity, right? Well, you can tell that these are particular cases of this. It could be maybe the Galilei one, the one that solves it. But I can tell you, I already told you that it doesn't, but that would be taking f equal to 0 and gamma equals to 1 and gamma tilde equals to 1 gives you exactly the Galilei boost. But let's see what the solution is when we plug these two things into here. So if we do so, we get the following equation. Right, this condition. So how did I get this? Well, all that I did is substitute the prime coordinates by these expressions, and I got this equation here. Now, the cool thing is that this has to be true for any two events separated by lights, any two. So, because this has to be true for any two events separated by light, all the coefficients have to be 0 simultaneously for the whole thing to be 0. So, this thing has to be 0, this thing has to be 0, this thing has to be 0. And that gives me condition 3 equations, and it gives me the condition for the 3 coefficients, f, gamma, and gamma tilde. Well, I'll leave the arithmetics for you as an exercise. And let's see what we actually obtain. This. So we find the value of f to be minus v over c squared, the value of gamma tilde equals the value of gamma, being the Lorentz, what is called the Lorentz factor. And the transformation is this one. Remember that we assumed that the velocity here had the direction of x. Okay? This is what you've learned as the Lorentz transformation. The thing that definitely you have seen in previous courses. If anything, you've seen this. And we obtained that, and this transformation is very different from the Galilei boost. In particular, also, this was assuming that the velocity is in the direction of x with a loss of generality. Let me write the expression for a velocity in an arbitrary direction, which is just rotating this, or alternatively deriving from the beginning that and getting more equations. You will get more equations, but you will solve them, and you will get the same number of the coefficients that have to cancel as you have unknowns in those equations. Let me write the general solution. I don't even know if you've seen in previous courses the expression for a velocity in an arbitrary direction. Let's have it. So this is the transformation for an arbitrary direction of the velocity, v. And well, I'm going to go on a limb here and guess that you haven't really seen this in previous courses. You've probably only seen the cases where the velocity aligns with one of the axes. By knowing that, of course, allegedly you can just do rotations and get the proper one. And obviously that's why we said without loss of generality. But usually people, if I ask you the t, you usually guess right, because it's just in a way, putting vectors on the thing, in a way. It's easy to guess. Now for the spatial one, many people screws it up. They forget this term here, okay? And that term is important. Now let's quickly check what happens. Let's quickly do a consistency check. Does this reduce to that? In the case that the velocity is this, I mean, I've been asked many times, like, but that thing kind of reduced to that, right? Well, let's see if it does. Let's compute, in this case, okay, let's just write what x is. X is a vector with coordinates x, y, z. Then v is a vector with coordinates v, 0, 0. Okay? And in that case, we know that v dot x is just x times v. Okay? I also know that v squared modulus squared is just v squared. Okay? And with that, I know that v dot x divided by v squared, by v squared times v, all right, it's going to be, and let me write it, this thing is x times v divided by v squared times v 0, 0, all right? So two v's cancel the two v's, and all that I'm left with is x 0, 0. In this particular case, this vector is just x 0, 0. Well, let's see what happens when I substitute here. The transformation will tell me that x prime, y prime, z prime, it's equal to x, y, z plus gamma minus 1, the vector x 0, 0, minus gamma v 0, 0, t. All right, so let's extract the three equations. What happens with z? Well, z prime equals z. That's easy to see. It's only this. There's no components here. Y prime equals y. Also easy to see. 1 here and 0, 0 here. What about the others? Well, what about x? X prime is, and let me write, 1x that I have from the first term, plus gamma minus 1, gamma x minus 1x, minus gamma vt. Right, this cancels this, and I'm left with gamma multiplying x minus vt. There we go. Exactly that case. All right. So this is the expression for the Lorentz transformation. The Lorentz boost. I call it Lorentz transformation, but maybe I should call it Lorentz boosts better, because we will get Lorentz transformations are more than just the boosts, as we will see when we study the Poincaré group. Okay, but these are the Lorentz boosts when the velocity goes in an arbitrary direction. Two more things to finish this video. First of all, we're going to quickly see the notion of composition of velocities, which is something that you've seen in your previous courses, but probably not for arbitrary velocities, right? So this notion is, okay, let capital V be the speed of a particle as measured from the frame S, which has coordinates tx and prime coordinates. And we have another reference frame S prime that differs from the first one in a constant speed. It's an inertial frame that has a constant speed, okay, with respect to the original one. And the coordinates of the other frame, the boosted frame by a velocity v, is st prime x prime, the prime ones. Now we know in the Galilei transformations we know that, of course, the velocity in the new frame would be the velocity that has in the original frame minus the speed of the frame. That's the composition of velocities, right? If you throw a ball from a train, the velocities add, so it's just putting this on the other side, right? Okay, so let's compute what would be the case for the Lorentz transformation. What is the composition of velocities, all right? So what is V? So we know that V is, of course, the variation of the position with respect to the time in that frame. So capital V is dx without primes dt. Wonderful. What is capital V prime? Well, capital V prime is the same thing, but from the reference frame of the prime system, right? T prime. All right, so we can actually use chain rule here. So this thing is equal to dx prime dt, and now I have dt prime, right? Or in other words, we have that this is dx prime dt, and then dt prime dt to the minus 1. All right, why did I write like that? Well, because we have these formulas here, and we can just differentiate these expressions, right, to get the expression that we want for capital V prime. So that's very easy. I mean, it's just a matter of arithmetics and taking derivatives, and remembering that every time that you get dx dt, you substitute by capital V, okay? So the result of doing that is the following, which is probably more complicated than the ones that you remember. We will get there in a second. But you can also check how, well, first of all, please do the calculation yourselves. It's very easy. You see, when I take the derivative with respect to t of here, I had a t, that's 1. When I get an x is dx dt, which is capital V, all right? I also try to make the capitals very visible, adding a bit of a sharifa to the capitals. Anyway, so you can tell that for low speeds, for speeds that are small as compared to the speed of light, this thing becomes the Galilean one. How do I see that? Well, if v is small with respect to the speed of light, gamma is 1, and also this factor is neglected. So this factor is neglected, this factor is neglected. So this becomes, the denominator is just 1 in that approximation, gamma becomes 1, so that cancels, and then gamma becomes 1 here, and you recover the Galilei boost composition of speeds formula, of velocity, sorry. Now, the ones that you remember are usually considering the velocity in the direction of the x-axis, right? Now, we can decompose this, and this is a good exercise. Some years I've given it as an assignment, some years I haven't. As an easy part of an exercise of an assignment is decompose this into a transformation for the parallel component of velocity to the motion, so in two directions. The direction of the speed of the frame and the direction perpendicular to it. We can decompose it in these two components, that's easy. To get the perpendicular one, to get the parallel one, you just take the dot product with respect to the velocity and divide by the norm. And to get the perpendicular one, subtract the component from the parallel one. So what we obtain doing that is the following. This one here. So I decompose the velocity into a component that is in the direction of the velocity of the particle, I decompose in two components. One that is parallel to the direction of the velocity of the frames, between the frames, another one that's perpendicular to the velocity between the frames, right? Now, this is the unit vector in the direction of the velocity of the frames. Now, of course, the parallel one gets transformed, and this is the transformation law, and this is probably the thing that you remember from your transformation laws that you've seen in previous courses. The one thing that many people make mistakes with is that they think, oh, the perpendicular direction, right? If the particle, the directions of the velocity that are not in the direction of the velocities of the two frames don't get affected, because remember, we saw that if the velocity is the direction of x, the y and z components don't get transformed, right? Well, that's not true for velocities. Why? Because look at what the velocity is dx dt. And even if the components of the x don't change, the dt do change, if you want. The differential of time, if you want, changes, certainly. I mean, I'm speaking roughly here because we will see differential geometry later on. But basically, the time changes, and therefore, the variation with respect to time will be different. So there is a transformation of the perpendicular components of the velocity of the particle as well, perpendicular with respect to the velocity between the two frames. All right? Okay. So just one last thing before we finish this video. All right, one last thing that we will see before finishing this video is that the space-time element between any two events, in this case, it doesn't matter if they're light connected or not, any two events, and we will talk more about that when we see the Poincare group a little bit better, is invariant under Lorentz boosts, under rotations, under translations, and under time shifts. Under rotations, very easy. This is the modulus square of the spatial distance between the two events. So that's invariant under rotation, is the magnitude. Also invariant under translations, right, is the delta. So if I shift the two coordinates, nothing happens. The distance keeps being the same. It's invariant under time shifts, the same thing, is the delta t here. So if I shift the two times the same amount, nothing changes. And it's invariant under Lorentz boosts. And that's something that we'll actually see in the course when we're gonna play a little bit with Mathematica after seeing the Poincaré group, but you can check yourselves very easily with the transformations we derived. This thing is invariant. Now, you can tell that this thing is going to have a meaning. This is the thing that captures if you want, the symmetries of the space-time transformations, the boosts, the transformations between inertial reference frames, the boosts, the rotations, the translations, and the shifts. Now remember that we derive these Lorentz boosts out of demanding linearity of the transformations. And I didn't make a big deal out of that, but it's a bit of a big deal because there could be non-linear, you can ask, are there non-linear transformations that work here? That's a question that I asked the first time I was taught special relativity, and the professor said, interesting, I don't know. So I tried, it's easy to cook up a non-linear one. Let me give you a non-linear transformation that leaves this thing invariant and captures the same. It will actually be respectful with the postulates of special relativity. Let's see. All right, so let's take a look at this thing that I call a nonlinear boost here. So what happens with this? I define the transformation here as if it were a Galilei transformation, but then I define the transformation of time in this particular nonlinear way. And with this kind of transformation, you still satisfy the second postulate of special relativity. So if the transformation were like this, then you plug them in, you just compute it, and you plug them in here, and you get this expression too. You get that for two different frames, if two events are separated by light, by propagation of light, delta S squared is 0. Now there's a difference though. This transformation doesn't leave the line element invariant like the Lorentz transformations do. But okay, that's not something that I demanded at the level of postulates. Remember that my postulates are only related to observations on the propagation of light, that the speed of light is the same for inertial observers. So why? I mean, this thing would satisfy the postulates. Why are we not using this instead of that? Well, there are several answers to this. Answer number one, you can actually do experiments and find out that these are the right ones, and therefore, okay, argument settled, this is not right. But it's funny, because what is the reason? At the level of postulates, I needed to postulate the linearity of the transformations to obtain this on top of the second postulate of special relativity, because the second postulate could also lead to a transformation like this. See what I mean? So I would love to find a good argument to say that the transformations have to be linear. There are some arguments along those lines, and those arguments are related to isotropy and homogeneity. But again, they're usually not mentioned in courses in special relativity. Let's take a look at those arguments. All right, consider two very, very close events, not necessarily separated by propagation of light. So I consider an event Tx and another event t plus small amount dt, x plus dx, small amount dx. Right? I want to write things in terms of differentials, in terms of what we're going to call the line element. Now, the space-time interval between them now becomes a differential space-time interval between them. Again, this is a little bit less rigorous than what we will do during the course because we haven't seen differential geometry yet. But this is the typical way in which we proceed analyzing events that are differentially separated from each other in the context of physical setups. So following this, we can compute the small. Think of this instead of a differential. Let's not take the limit yet. Think of it as a very small separation. Then, of course, we get that this is minus c squared dt squared plus dx squared. All right. Now, we know already that ds squared prime equals to 0 equals to ds squared for two different reference frames, okay? So, of course, you would have the equivalent now in a different reference frame with primes in here, and the same one with primes in there. Now, for both of them, we know that for the propagation of light, for light propagation, they're 0, both of them. And we also know that they're differentials of the same order. So, argument by Landau. Because of that, we know that ds squared has to be equal, ds squared prime, if you want, has to be equal to some function, let me call it f, or maybe omega is better, some function omega that may depend on t, on x, on the velocity between the two frames, ds squared. If we want not to give any particular importance to any particular points of in spacetime, then this transformation factor, this difference between the delta s and the delta s prime at a differential level, will have to be given by something that cannot depend on the point in spacetime. So this, demanding that it will not depend on this, it will be demanding homogeneity. Homogeneity. If we demand homogeneity, then the transformation of the spacetime interval cannot depend on t and x. If on top of that we demand isotropy, which is, well, the transformation between ds prime and ds cannot depend on the direction of the velocity, then demanding these two things would have that this factor would be dependent only on the modulus of v, ds squared. Now, again, this demand is saying, well, the spacetime interval between the two events cannot depend on the point of spacetime, on any point, cannot be different, this factor cannot be different in different points of spacetime. Why? What would be some that would be special with respect to others? And also cannot depend on the velocity, in the direction of the velocity of between the two frames. If we do that, we get that the transformation between the two differential small spacetime intervals, ds squared in this case, has to be a factor that depends on the velocity, on the modulus of the velocity. If we impose that condition, if we say, okay, whatever this has to be the same when they're when they connect the propagation of light, and they have to differ by a factor that cannot depend on the point of spacetime. What would it be different, the laws of physics at every point of spacetime? And it shouldn't depend on the direction that you pick for taking that speed. Why would it be different in different directions? So homogeneity and isotropy, demanding that is like, well, still can't depend on that. Actually, you can prove that there's only one transformation that does it, and for that transformation, this is one, and this is the Lorentz boosts. So for that transformation in particular, you get that assuming homogeneity and isotropy, there's only one transformation that this is the Lorentz boosts that we found. Right, anyway, to get that argument, still remember that we have had to make an assumption on homogeneity and isotropy that was not there in the postulates. I remind you, the postulates only talk about the propagation of light and speed being the same for all inertial observers. That thing is needed as an extra postulate. At the very least, this argument of homogeneity and isotropy, if you prefer, you can postulate, I want the transformations to be linear, but it's the same. Now, a little note for that will be helpful later on in the course. We will revisit this, because actually, as you can tell, the group of transformations that satisfy that they're connected by light, that the two events connected by light will have zero spacetime interval, which is the mathematical expression of the postulate, gives you a set of conformal transformations. We haven't seen yet what conformal means here, but a transformation where the spacetime interval is scaled by some function. Now, of all the set of conformal transformations, you could actually have said, oh, because of that postulate, I know the reference frame transformation should be conformal transformations in that sense, transformations that satisfy that the line element is related like this. If I also demand homogeneity and isotropy, then in the dependence on that conformal factor, then I get that the only possible transformation is the Lorentz boosts. I would love to discuss this much more in the live sessions, and please let's do it. But I left it there, and also as we learn more differential geometry, we will be able to come back to this and discuss it a little bit, because I think it's super interesting and it's very important at the level of theory building. So anyway, let's discuss this in the future. Alright, so that's pretty much it for this video. That's all that I wanted to tell you. I'll see you in the next video to talk about the notion of proper time, and then talk a little bit about the Poincare group and understand a little bit better what is the group of transformations between different reference frames in special relativity, probably in ways that you haven't seen in previous courses. See you then!